Today I'll be sharing with you all Core.logic with with Sudoku. So maybe I would share some things about myself first. So my name is Zachary, for those that don't know me, and y'all can call me Zach. And I'm based in Singapore, and I'm actually the organizer of this Clojure Asia Meetup, which I sort of started off in November 2021, first as um, sort of pitching within Singapore, but seemed to attract a more diverse crowd beyond Singapore. So I ended up pitching it as Asia as a whole, and I think that has grown through the months. Yeah, and recently I started streaming on Twitch under a sort of handle of programmer Teo, and trying to sort of grow that and maybe make some videos and I'll see how that goes. I think it also helps me to um, practice Clojure uh like in my sort of free time, while also like motivates me to practice Clojure. Yeah, and I'm proud to say that I'm somehow managed to find a sort of Clojure full-time role within uh the company I'm currently working at, called DBS, also known as Development Bank of Singapore. And yeah, so I've been working with an application, a Clojure application that uses XTDB on the back end, and so doing like some metadata replication of sorts. Yeah. Okay. So maybe y'all might be wondering um, why I want to talk about Core.logic. So for my own personal motivation into why I wanted to dive deeper into Core.logic was for the sake of um, firstly, uh, I think expanding horizons a good thing, which is why, like, I guess we picked up Clojure, right? Because maybe you started off with like your typical more popular languages like Python, or maybe some exposure to the different C languages. But then you saw that Clojure was a thing, and like then you exposed yourself to functional programming or like Lisp in general. And so I think widening that horizon with logic programming is definitely something would that Clojure programmers would also, like, having learned Clojure, would also understand that maybe that's a good idea. Um, then I felt I'm quite exposed to data log because of my usage in XTDB for work. So um, I think for that for sorry, give me a moment. So for that, um, I felt that logic programming isn't too far off from what I know and am exposed to. And in school, lastly in school, I sort of did some work with like solvers. So solvers in terms of like linear programming, sort of like operation research kind of things. So people would sort of model their um, mathematical problems in a sort of like and using sort of similar ideas of like having a goal, or maybe like a target that you want to increase or decrease, and having certain constraints and letting the solver do its thing. Yeah. Okay, next slide. Okay, so for those of y'all who are new to logic programming, which I think most of y'all are somewhat, um, so I think with any logic programming involves, like, instead of like conventional programming where you already have you need to write your own logic. Um, what logic programming entails instead is for you to give a goal that you want to find, and sort of list the sort of constraints that you have for that goal. And there's an internal sort of like solver engine that will help you resolve the to find what you want to find. And I think the closest analogy that you all might be familiar to is the idea of using SQL to query your database. So SQL is like the domain language that you sort of write, but the actual logic that goes into handling the selecting, the combining of the tables and whatnot, it's handled under the hood by the relational query engine rather than on your own now. So Core.logic and by extension, logic programming and by extension, Core.logic does something similar. So you need to specify a goal, so or multiple goals. In this case, like various like logic variables, and then you specify the various constraints, of which like you'll probably say, you'll probably mention the logical variables in those constraints lah. And one of the things that I'm highlighting in every slide is sort of like the syntax, um, that new syntax that you might see. So in this case, it's like logic slash run star and logic slash run. So uh, for core.logic, you'll always be writing code within the confines of this. The main code will be inside confines of this run star function, because the logical variables and the expressions don't really mean much outside of that. And if you're wondering what logic slash run does, is that if you do logic run star, it'll give all the possible combinations. But sometimes you only want a single solution, so you do like logic run one, and then similar syntax. Yeah. Okay. So some other things to uh, yeah, as I mentioned, some of the things are that there's very most functions have limited meaning outside of this run slash run star. Um, this is for all your core.logic functions. And something interesting, which is, I believe, taken from logic programming in general, is that there's a certain naming conventions to all like this core.logic functions. So differentiating from like your normal Clojure functions, you'll often append like the vowels except for I. And so, for example, you end up with like from cons, you got console, you got conj to conjo, and rest to resto, and so on and so forth. Like even defen becomes defeni kind of thing. Yeah. So that's something interesting. And apparently um, this helps a lot when you start combining logic programming functions along with functions along with normal Clojure functions, and especially as you make a more extensive, more comprehensive uh, logic program of sorts. Okay, so some simple code to get you started in that sense. Um, Maybe like if you see the first block on top, um, so you have like you specify this goal of finding Q, and you do something as simple as saying that, okay, Q will be equals to 1. So in that sense, you can solve it and you'll get 1, which, okay, is but then maybe there'll be cases where you might specify that Q is both 1 and 2. But logically, this is uh, impossible, which is why the solver will return no results. And there's a case where if you use the con like the con the function, that you can then say that, okay, if the first path doesn't work, then you can also there's also the second path. You so show the results from both paths in that sense. So you say that Q can take both the value of 1 and 2 actually. So that's how you use this function. Okay. So something more, perhaps a bit more interesting as you build up, is that if we want to say model 2 coin tosses, say like you toss a coin, you get heads and tails, and maybe you toss another coin, you get another heads and tails. So how might you model that? So similar idea, except now that instead of finding just Q, we are finding 2 logical variables, which we call like coin 1 and coin 2. And we specify to say that a coin domain only has a coin will be of sort of values 0 or 1 in this sort of domain. And we're saying that, okay, for my logical variables, coin 1 and coin 2, they belong to this a 0 or 1 domain. So you have these are the total all the possibilities, all possible combinations of the values of these two coins lah. That's what you'll get. And so you can sort of think, okay, maybe I can say heads is 1 and tails is 0, or vice versa, depending on what you want. Some interesting functions to note is like this domain to sort of like limit the search space within your logical variable, as well as this like fd in this is also part of Core.logic. I think it's Core.logic. Then F is it's another file in the same library. Yeah, and this in and the domain comes in conjunction with one another lah. Yeah. One last thing is this let. In Core.logic, uh, if you define things unlike normal Clojure programs, if you have like global variables which you def out outside of your run star function, those will not work. I believe you throw an error. So you need to do local bindings with a let, and maybe inside the let, then you say that coin is maybe, and then you have defined coin above as a global variable outside of it. Yeah. Okay. So next slide. Okay. So modeling two coin tosses like continued. So another way we can do this is we can have again coin 1, coin 2, but then now we specify it manually like coin 1 is this, and we repeat the code, so it'll be the same thing. But it also can be rewritten as you can use this every g function. I think the closest idea of this is that of like a map. So you can like map through all like the elements and say that all of them belong to like this same domain of 1/2. And this is something we'll use later on as we sort of solve the Sudoku problem. Yeah. Okay. Then some more simple other simple stuff is so we have this idea of like cons, right, which is this idea of you can cons one item to one element to a collection. So then this is what you return now, 1, 2, 3. So you can use those like equivalent functions that Core.logic has, like resto, console, and then you can do something similar. Just that in this case, maybe you would do, you will sort of say that the goal, you put there's a third argument, which is saying what's the output, and you put your Q there, and then that means your Q will be 1, 2, 3. So this kind of like okay is like okay, so call a lot like not too much to logic programming. Why can't I just use cons, right? So I think now you sort of see like the next part, which is like pretty magical, is that okay, so we can put Q here, right? But we don't have to put Q here. We can put Q anywhere else as well. So we can put Q to the front here as the first argument, and what you will get is okay, what do I need to append, what do I need to cons to 2 and 3 to get 1 to 3? Oh, it's 1. Then say instead, okay, if not, we know what collection we need to append to 1, 2, so we get 1 to 3, so we get 2 and 3. And we cannot just it doesn't have to be just the argument itself, it can be within the argument. So in this case, like when you cons 1 to the collection 2 and 3, you can ask what is the first element that you actually get. Yeah. So I think this sort of like a magical moment into the power of like logic programming. And I kind of was reminded of like box dude refine, but I understand that is slightly it's not using logic programming actually, but it's sort of like what I immediately thought of. So what that is like it allows you to sort of specify the input and the output, and then it will sort, it's a website or like it's a library that will give you possible functions that you can use to get from that one point to another. Yeah, which is quite interesting. Okay, so now we can talk about Sudoku and its rules. So I think Sudoku is a pretty well-known problem, but just to give a refresher for those that might not be as clear. Um, so I think a very quick way to describe it is within the rows, each and every of its 9 rows, as well as each and every of its 9 columns, as well as each and every of this square, like this 3 by 3, 3 by 3, 3 by 3 square, you cannot have any duplicates, and it needs to contain the numbers 1 to 9. Meaning to say that if 9 is in this row, you cannot have 9 here or here, or because this is belonging to the same row, you cannot have another 9 in that same column, and you cannot have another 9 in the same square. Yeah. So now let's try to translate these rules into modeling our problem in Core.logic. So same idea, we are concerned about the rows, the columns, and the squares. So just now I was talking about the in and the domain functions, fd domain, fd in. So just now I sort of did like a simple one where it's like heads and tails, right? Where it's either 0 or 1. So instead, we can say the domain will be 1 to 9, where the values will belong to of each and every cell will be will need to be of value 1 to 9, one of those values. And we want to give this this condition that each of the rows, columns, and squares are distinct, and there is an fd distinct function. So one last thing is that there's actually this logic slash lvar, which represents logical variable. So what we can do is we can create 9 times 9 logical variables, and um, thereafter we can group them up to their respective rows, columns, and squares to then give those distinct constraints, as well as like apply this domain constraint onto each and every cell that we specified in those 81 logical variables. So sort of like another note is like, okay, maybe Sudoku is okay, but like what if we sort of scale up? Maybe you kind of, I mean, it's like n Sudoku dash n lah. So it's like, or maybe you could do a 4 by 4 Sudoku, or 16 by 16 Sudoku, or you can do a 32 by 32 Sudoku. Yeah. Okay. So I'm going to do a quick demo. So I believe you all can see my Emacs screen. Let me close this and let me increase my screen size. Okay. So give me a moment. Okay. So this is the Sudoku function that I created, but let's try to break it down. So let's copy out this let block. So I think I'm taking a lot of reference from other Core.logic implementations of this Sudoku problem. One of them was like from Joy of Clojure, and one of them is from a primer that I'll mention later. So it's part of the wiki. So we can create logical variables, and 81 of them. So this is a Clojure function that oops. Let me check if I can. Oh, okay. So we can comment this out, and we can say if you want to see what vars is. Oh, let me define the other functions first. Let me evaluate the other functions first, and now get back to this. Okay. So if you want to find out what the repeatedly 81 logical vars does is that it creates 81 instances of this logical vars. 81 comes from 9 times 9, right? So we're defining every single cell inside the Sudoku board as a logical variable. So because these are things that we want to change and then we want to subsequently find the solve for. Yep. Then next we can group them into the rows, the columns, and the squares so that we can then apply the constraints upon them. So quick thing is we're just taking we're just partitioning 9. And I think from what I believe is that each of them needs to be in a vector. So it's a vector and a vector. So this is what we get. Let me increase the size and put this here. Oops. So now we have like 9 rows. And then from these 9 rows, if you do an apply of map on vectors, then you'll end up getting each of the columns as well. So you notice that now it's 1, 1, 2, 5, 2, and so on. Okay, let me just evaluate the columns. Oh, I think it'll change lah, but so now this is the columns, and the squares logic is a bit more confusing. So basically, we have x and y if we run squares. So we are first getting like the top leftmost of point of each square. So the first square will be the 0, 0 point. Next one will be 0, 3, 0, 6, and so on and so forth lah. So in total, we have these 9 squares, and basically we are getting the logical variables of each of these squares by taking from that top leftmost point. You also get the +3 from to its right and to its bottom in that sense, and then you'll get the 9 squares. Oops, sorry. Yep. So this is really just the setup, but and to help to organize our code better. Theoretically, which you probably don't want to do, is you could manually define out 81 variables and then manually write down, okay, that'll probably be like 9 times 3 conditions lah, where you manually key in, okay, A1 is A1, A2, A3, A4, blah blah blah, has to be distinct, and then and so forth. Okay, so this is just helping to automate that. Yeah. So now we can look into the brunt of the logic, the constraints. And we'll get to the other function that I created here later. So one thing you can do is you can still specify like one variable like q, but you can say that, okay, q is the same thing as all the vars that I put in my let binding lah. So basically q is not just q, you're actually getting all 81 vars. And then the next thing that we are doing is, as just now I was saying, we can map across all vars and say that they belong to the domain of 1 to 9. Yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. And so each of these vars can only have a value of 1 to 9. And we can skip this binding thing later. But the other rules that we had were for every row, which we sort of defined earlier here, and every column and every square, we want each of their values to be distinct, meaning to say that if I have 1 in the row already, I cannot have another one, and so forth. And the last part of the Sudoku problem is that they're not so mean to give you a empty board. In fact, if it's an empty board, maybe you have like a ton of multiple solutions. So now this binding function, what it does is really to take a board that of hints and then map it across to say that, okay, if it's if it's not a zero value, then let's say that that variable that we have will be the same value of the hint. So if we have a board, so if we have this hint like so, um, so once it reaches the 8, it will say that that logical variable that corresponds to this 8 will be of value 8, and so it's sort of fixed already lah. It's another constraint that we need to add to help ourselves and make the solver run faster. So, oops, more people joining. Okay, so yeah, and we're just really mapping across this. And I think this just now I was saying, if it is non-zero, then it will be that value of the hint. But if not, I believe you need to just say that it will just have a succeed condition. I think it's just to prevent an error from throwing. Yep. Okay, so can evaluate everything. Okay, I can quickly delete this because this is the main Sudoku function. So same idea. Another only thing to point out is that now we're not doing run star. Theoretically, you can do. Let me just show you run one first. So we're just getting the first solution that the solver gets. These other two functions are just to help me print out the solution. Okay. So if we define out this hint, so this is a Sudoku the starting Sudoku problem in that sense, then it's not the neatest, but you kind of get the idea. So 0 is like empty, and then like the numbers are for like numbers from 1 to 9 are the what is already defined for you so that you can have a starting point. So if I run this hints tree on the prep and the print board, it will help me print out the board as shown here. So this is our starting Sudoku problem that we have. So just now corresponding 8 and so on. Yep. So now we can really just run this okay, we can actually just run this first. So it'll give the results in this form. It's not great. Yeah. So we want to get the first still inside a collection. So we get the first, and then we prep it so-called to help the printing function, and then if we print it out, this is the solution to the problem. Yeah. So you have can look at here, I guess. So okay, wait, I can drag this up and then you can see. So pretty fast, I would say. So all the hints that it has will still be in the same positions because we constrain them with the binding function that I did earlier. Yeah. And okay. So just now I sort of like hinted at, okay, maybe we can do Sudoku problems which are bigger. So I'm a bit lazy to define the other hints in this board. So like we can do a hints dash like a Sudoku question for 4x4 or Sudoku question for 16x16. I also did a 32x32, but it sort of will crash because I think I'll heap memory, and because I'm too lazy to input every single item of a possible 32x32 question. It can kind of get quite difficult to do that. So maybe there's a different problem altogether. So now I'm just changing the get square function to have this n to say like what type of N Sudoku is it? Maybe so the N2 Sudoku would be like a 4x4 board. So the normal Sudoku is a N3 Sudoku. Not too much changes. Just I'm creating the board. So N3 Sudoku, your normal Sudoku, when you square it is 9x9. And so I'm just saying, so 9 times 9 logical variables. So now instead, it'll scale accordingly. Yeah. And changing a bit of the prep functions and the printing functions. And we can solve uh, the small 2x2 board that we had. So just now I had the 0 and 2, and then it sort of filled up the rest on its own. Yep. And then I can do it for just now, which we already did, the conventional 3x3. I don't 9x9, I mean. And then we can also do it for the 16x16. Yep. I was lazy, so I only put like 0, the hints of 1 and 2 here, but it's sort of like solve the rest. Yep. Okay. I think the only last interesting thing to show is if we change the hints to, if we change it from run 1 to run star. Actually, I should just change this one. So just now to our normal Sudoku function, we can just change this to run star. So for those of you who don't know, apparently some Sudoku problems, especially the easier ones, they have more than one solution. So we can test this out by running this Sudoku function on this hint that we have. And we can see that, okay, I shouldn't print it out. I should just just run this. Okay, it's only have one solution. But if we had an empty, let's say we barely had any hints, we can use the hints tool. Oops. Is it running? Oh no, I think it's too many solutions. Okay, that was a bad idea. All right, but I didn't give an example for this, but basically when you change from, oh, I guess I can run to, oh, sorry, give me a moment. So instead of putting run star, I'll put run 2. And let me restart the repo. Okay, so this can define this. Okay, so yeah, you can see that it has actually 2 solutions now. From this hint of like 0, 2, and whatnot. Yeah, it's not the full board, but you kind of get the idea, I suppose. Yep. Okay. I can go back to the slides. I hope that was a relatively good demo. Full screen. Okay. Okay. So some pointers I want to conclude my talk with. I think as I myself ventured into the domain of Core.logic, which I don't claim to be any expert in, far from that. I would say that there's really like similar to how when you started off with Clojure, um, we might be still like thinking of our for loops and um, so maybe the first thing you search for is for, and then we only think of it in that terms, but actually there's like things like your map, your reduce and whatnot. So there's a lot of new vocabulary to learn, and you need to sort of know that to be able to model your problem in the best way lah. So I sort of like went through some of the functions that are available, but there's definitely much more that I've not covered. um, and then I think something I sort of realized that actually a lot of like Clojure docs within the Core.logic sphere is not documented. So I guess an opportunity actually, so that like if you're any like interested to venture into Core.logic, you can contribute to the community by like giving examples in Clojure docs or linking like the C also, or giving some notes there. And I think that would make the documentation within our community richer, and I think definitely stuff that good ways to contribute. Yeah. So um, I guess for those that are perhaps have gotten interested from this sort of like short demo that I've had, short talk that I had, um, some of the things, some of the resources to start you off with are the Core.logic primer. This is within the Core.logic wiki, and I guess the Core.logic repo, GitHub wiki itself. So it'll go through some of the the examples that I showed earlier, as well as like walk you through what is logic programming about and how it works. And they sort of like strive to give you this aha moment to logic programming lah, and what are the possibilities that you can do with it. And if not, um, can also thereafter you can try to model, I would say, perhaps games with it with well-defined rules, such as in this case like Sudoku. But there's a lot of other logic games that you can work with. I think it's just that perhaps Sudoku is one of the simplest because you can easily do the every G thing to get you can easily get the rows and columns and the squares somewhat easily, as compared to say one which you need to find uh, manually define the board lah yourself, or you cannot find any pattern in that sense. And another pathway I would say that is sort of the route of data log. I would say that it's not entirely linked, in that Core.logic is logic programming is like no core data log is a subset of logic programming. But I would say that in terms of use case, perhaps data log is something that is fairly regularly seen within the Clojure community with all the graph databases that we have. So, and I think it's definitely something that's quite interesting. Um, yeah. Uh, on that note, also though, yeah. So if you want to study data log, which this talk isn't about, um, you can look at the like learn XTDB data log today, or there's learn data log today lah, but the XTDB one is one where they're using XTDB for it. And interestingly enough, I think Jeremy from the XTDB team also dropped me a PM sharing a GitHub gist where he actually tried to do the Sudoku problem within data log. It's fairly convoluted, as in he wanted to tidy it up and whatnot. He hasn't had the time, but also will link it in the chat later. So if not, yes, we're done. Any questions? I hope you all had a good talk. Okay. Thank you.